Hi there, welcome back to the second half of this term. I hope you had a productive half term. I've learnt myself a few tricks. Actually, that's the only trick I've learnt to do. Moving on. Right, we look at in chapter 19, it's another chapter about the forces in the title, but it's going to incorporate what we've done before in the forces in chapter 18, and it's going to incorporate the kinematics we've done in chapters leading up to that point. So it's Newton's third law we're looking at. We're looking at the forces on two objects which they're in contact with each other. The Newton's third law says if A exerts a force on B, then B exerts the same force equally but in an opposite sense on A. If you push against the wall pushes back on you, etc. So, often expressed as every action has an equal and opposite reaction. It's a good example of it is this person is pushing on the wall. So this force here is the force on the wall. So if I was just drawing the wall, I would have the diagram of the wall with that force on it. If we were drawing a picture of the forces acting on the person, we would draw the person and we would have the same force in terms of size but opposite in direction acting back on the person. Okay, and this bit here I'm trying to make sense of what they mean by since the force is away from the wall you might slip backwards. I guess if you're pushing hard enough you might find just your feet slipping back away from you. That's the only sense I can make of that sentence. Important to remember is, and they emphasize this in the book, the two forces in Newton's third law don't act on the same object. So if you've got two objects in contact, you've got one force acting on object A and the equal and opposite force acting on object B, okay? So if you draw the forces acting on A, you don't put both forces on that diagram. If you draw just the forces on B, you don't put both forces on that diagram, okay? If you want to draw them both together, then you can't confuse them acting on the same thing. When's that going to be important? It's going to be important when we've got something sat on a surface and we might be drawing the weight acting on that object and a reaction with the floor. Reaction and weight aren't a pair in the sense of action and reaction. We're going to come to that in the second lesson this week. Right, there's only one example before exercise 19a. You could read it, it's on page 398. Two ice skaters. We're going to see a lot about ice skaters, robots, and I think bumper cars coming up in the very short exercise. They push it against each other, so they're holding hands and they're pushing each other apart, but they're in contact, so they're pushing away from each other on the ice. They're on the ice, there is no friction on the ice. So as they're close together and they're pushing each other apart. First skater has that mass and this acceleration, which is in that direction. The second skater has this mass, and because the masses of the skaters are different, but the size of the forces will be the same, this is the Newton 3 bit, the acceleration of the second skater will be different. So how do we do this? We clearly state that we're using Newton's second law for skater A, which gives us a force of this size. We then state Newton's second law for skater B using the same size of force, but notice for skater A, the force and the acceleration were both that way. For skater B, the force and the acceleration are both this way. So we end up with this acceleration. Skater B weighs less. Skater B's acceleration has a greater size whilst they are in contact with each other. Now, don't try not to be confused by this. They've said draw two separate force diagrams. I think what they want us to imagine is that you hadn't drawn the ghost skater on the right there, and you did not draw the ghost skater on the left there. That's what it means by the separate diagrams, if you're confused by what they're talking about. That's it in terms of the notes. So let's see what we want us to do. Just that idea to start chapter 19, but even though we're introducing Newton's third law, we've straight away still been Newton's second law. And if Newton's second law connects force to acceleration, then we could be using our kinematics once we have an acceleration. If all the forces are constant, and the masses will be for all the work we do, but there is some interesting work involving changing masses, but not on our course. If the forces are constant, then the accelerations are constant, and it will be the Suvat equations, which you don't need to learn. They're on the formula sheet, but this might be a good time to have them written at the top of the page for when we do use any acceleration into the kinematics. In 19A, you have to assume the questions are for when the bumper cars are still in contact, when they're colliding and still staying in contact, pushing each one way or the other. Any questions about ice skaters for Newton's third law, they're either pulling each other together or they're pushing each other apart, but they're still in contact with each other, okay? As soon as they let go, that force, contact force, disappears. So this is all about things being in contact. An interesting point made in question 5 is actually about gravitation. The point about gravitation would be Sun, Earth, they're not in contact, but there is a force between them, and the force of the Sun on the Earth is equal to the force of the Earth on the Sun. Okay, so there's a bit about that in chapter 5 for interest. Only 5 questions in 19A, so when you've watched this, work through all of them carefully, check your answers. By all means, read ahead to normal reaction force, but that's where I'm going to start tomorrow. So, well, that's a record, isn't it? Less than 8 minutes. Good luck with 19A, and the key thing is it's only valid when things are in contact with each other. Right, good luck. Oh, and hopefully we'll be seeing you sooner rather than later now. But we'll wait to hear if there's any news about that this week. Okay.